All right. Hello, everyone. Welcome back to another one of my videos, and Merry Christmas if you celebrate. Today, we're going to be taking a look at a linear algebra problem, and it is a problem from the March 2010 comprehensive exam. It's question number 4, and it reads, find a matrix P and a diagonal matrix D for which P inverse AP is equal to D when A is this specific matrix that we have right here. Given that A has a characteristic polynomial, P of lambda is equal to lambda plus 2 times lambda minus 1 squared. So this is actually very convenient. They were very nice to give us this specific fact, right? Because we need to find the characteristic polynomial because the roots of that are the eigenvalues. However, if we needed to find the characteristic polynomial on our own, right, it would be much more complicated. We'd have to find a minus lambda I, take the determinant of that, and factoring might be a nightmare because it would end up with a cubic. However, we are given the characteristic polynomial, and with that, we can find the eigenvalues, and here is why that is helpful. So if you take a look at this equation, P inverse times A times P, I'm actually going to modify it a little bit because this is how I actually learned it. If we multiply both equations, or both sides of the equation, sorry, by P on the left and P inverse on the right, that will end up with A, right? Because the P inverse and the P will cancel out on both sides. It's equal to P times D times P inverse. And D is a diagonal matrix. And if a matrix is diagonalizable, we can come up with this decomposition for it, this PDP inverse, and D is going to be a diagonal matrix of eigenvalues, right? That's why we need the characteristic equation. Matrix of eigenvalues. And if it's a non-degenerate matrix with all distinct eigenvalues, it's guaranteed to be diagonalizable, right? And then our P matrix is just going to be a matrix of the eigenvectors. We also want the eigenvectors to be linearly independent from each other. That way it's invertible, right? So this is what we are searching for. And so first we need to find the eigenvalues to come up with our matrix D. So we need to find the roots, right, of the characteristic polynomial. So step 1 is eigenvalues. So I'm going to say eigenvals, right? And because it's lambda plus 2 times lambda minus 1 squared, right, that will give us lambda is equal to -2, right? Because we're setting it equal to 0, 1, and 1. So the reason I wrote 1 twice here is because it has a multiplicity of 2, meaning that we kind of have a double root in this situation, which is totally fine because when we find the associated eigenvector and eigenspace, it should have dimension 2. So there's going to be 2 eigenvectors that we can associate with that, right? So right now, we can actually create our diagonal matrix, right? So a diagonal matrix just has entries on the diagonal columns. Everything else is going to be 0. So because this is a 3x3 world that we're working in, it's going to look something like this. And people ask me, does it matter what order I put the eigenvalues in? And I believe that the answer to that question, although if you know this answer and I'm wrong, please correct me in the comments. The answer to that is no. However, you want to make sure that the columns of the matrix for P that have the eigenvectors line up with or match up with the associated eigenvalues, which is something that we'll talk about later. So if that doesn't make any sense yet, that's totally fine. So that is D, right? That is our diagonal matrix. However, we still need to find P, right? So P is our matrix of eigenvectors. So in order to do that, we're going to need to find the eigenvectors that are associated with each eigenvalue. Sorry. So the way that we're going to do that is we're going to find a minus, right, lambda I for both of our values of lambda, and then row reduce that and find a basis for the null space. Sorry that the lambda looks a little bit funky there. As we know, my handwriting is god awful. Okay, So a minus lambda I here, let's start with lambda is equal to -2. So that's just going to be +2 to all of the diagonals, right? And because A is this matrix up here, I actually went ahead and did this math out. That's going to give us 3, 0, 0, 2, -3, 2, and then 1, -2, 2. Awesome. And remember, to find a basis for the row space, all we need to do is row reduce. And this is actually quite easy to do if you're familiar with Gaussian elimination, which I'm going to assume you are. But the way that we row reduce this is not too hard. So if you're not comfortable or familiar with that, make sure that you do that, and you can just search Gaussian elimination to find an easy video on that. But what this is going to turn into, right, is 3, 0, 0. Nothing's going to happen to the top. 0, -1, 2, and 1, negative. Oh, nope. Just zeros on the bottom. Sorry, obviously, right? Because this is an eigenvalue, when we row reduce it, it should give us a 0 row. And it does. So that means, right, solving the equation, that should give us this following vector, where we have a free variable. Again, because the eigenvector is a basis of an eigenspace, there should be, right, a free variable, right? Because any scalar multiple of this is going to also be an eigenvector, right? It doesn't really matter about the length, it just matters about the direction. So this is going to be our first one. So this is going to be v of lambda 1. Or we can also represent it as 0, 2, 1, and pull out that alpha, right? Because this is what we really care about here. Awesome. Okay, so now let's do the following for our other eigenvalue. Remember, we're going to just find a minus lambda I, but here lambda is just going to be 1, right? So we're just going to subtract 1 from all of the diagonals, and the resulting matrix is going to be, oh, look at that, we have a row of zeros already. However, we're going to get another one actually, and I'll show you how that's going to work. Remember, this is a repeated eigenvalue, right? Lambda equals 1 has multiplicity 2. So we should expect, hopefully, to get 2 here. Otherwise, we'd have an issue. So when we row reduce this, oh, and I forgot to subtract, so let me subtract. So when we subtract 1 from that, that's going to be -4. This is going to be 0. This is going to be -2, and this is going to be 0. No, this is not. This is going to be 1. I'm sorry. I'm looking at the wrong thing here. Pardon me. 1, -2, 1. Okay, sorry, we're back on track, right? Because when we row reduce this, obviously, if we subtract 1/2 times row 2 from row 3, that's going to give us another column of zeros, right? Or another row of zeros, sorry about that. So it's going to look something like this. And here, right, when we solve the homogeneous equation to get a basis for the eigenspace, we're going to get 2 eigenvectors, and the solutions are going to look like this. So we're going to call this v of lambda 2, right? That's going to be 2 free variables now. We'll call them alpha and beta. And the first entry is just going to be 2 alpha minus beta. So 2 alpha minus beta. And then when we break that up into 2 vectors, right, that's going to be alpha times 2, 1, 0 plus beta times, I believe, -1, 0, 1. So now, right, we have 3 vectors, and I'm going to go through and highlight each of them in pink. We have 3 vectors that we can use to form our matrix P, right? So we have 2 that are associated with our eigenvalue of multiplicity 2. And then going up here, we have 1 that is associated with our lambda 1 equals -2. So the way that we designed our diagonal matrix, -2 comes first. So this vector right here, this 0, 2, 1, that's going to come first in our P matrix, right? So let us go back to the black marker and say that P, right, our first eigenvector is going to be 0, 2, 1, because that perfectly matches what we have here. And then our other two eigenvectors are just going to go next to it. So 2, 1, 0, and -1, 0, 1. Awesome. Now, let's write D again, just so that we can have our final answer in one space, right? 0, 0, 0, 1, 0, 0, 0, 1. So this is our matrix D and our matrix P, such that A is going to be equal to P D times P inverse. We can make sure that P is invertible. That is one way to kind of check to make sure things are lining up to be what they are. We can also go through and check our work just by multiplying this out, right? And ensuring that this does in fact equal our original matrix A. So this question is very nice in the sense that we can check to make sure our work is right. But a problem like this, just to summarize, basically just consists of finding the eigenvalues, which if they didn't give us this characteristic polynomial would be a lot more complex. However, we don't have to do any weird factoring. We can find the eigenvalues quite easily, create our diagonal matrix D. Then we find the associated eigenvectors with each eigenvalue and throw that into a matrix as well, making sure that everything matches up with the associated eigenvalue and eigenvector. And then we have our final answer, which should just be two matrices. If you'd like to check this out and do the multiplication on your own, feel free to do so. However, I'm pretty confident this is the right answer. As always, if you have any questions about my process or want any further clarification or elaboration on any of these things, definitely feel free to ask. And yes, until next time.